I'm Adam from RFOXiA from our real lab. Today we're answering why most BLE modules ship with their firmware sealed shut and what full open source access with SWD programmability actually changes for the builder who needs it. Enjoy our new soundtrack at the end of the video. Let me start with a fact that should be more widely understood. When a manufacturer ships a BLE module with locked firmware, that is not a technical constraint. The silicon does not require it. The radio certification does not require it. The choice to lock the firmware is a business decision. It protects the manufacturer's software investment, it creates dependency, and it ensures that every feature you need that they did not include becomes a future upsell or an insurmountable wall. The hardware is capable. The manufacturer simply decided you should not have access to it. The Multinav Pro Plus BLE module makes a different decision. Full open source firmware access, SWD programmability, and a processor architecture that was specifically chosen because it gives you clean, auditable control over your own application layer without compromising the certified radio stack. Let me walk through what that actually means. The module is built around the STM32WB07CCV6. This is a dual-core processor from STMicroelectronics. The first core, Cortex-M0 Plus, handles the BLE stack. The link layer, the HCI, the BLE timing engine. The second core, Cortex-M4, is yours. Your application firmware runs here. These two cores communicate through a shared memory interface that STM calls the mailbox. The BLE core manages radio timing, your core manages logic, sensors, control decisions, communication protocols, everything your application actually needs to do. Why does this matter for open source access? Because the BLE stack running on the M0 Plus core is certified firmware. It passed FCC testing as part of the module's certification. You do not need to touch it, you should not touch it, and you do not have to. The M4 core, the application core, is entirely open. You write that firmware yourself. You can read every line of it, modify every behavior, compile it with any toolchain that supports ARM Cortex-M, and flash it over SWD with a standard ST-Link programmer, which is included in the RFOXiA Power and Program Kit. SWD stands for Serial Wire Debug. It is a two-wire debug interface, SWDO and SWDCAG, that gives you full read and write access to the processor's memory, registers, and flash storage. This is the same interface used during manufacturing and testing. When you have SWD access, you can flash new firmware in seconds, you can set breakpoints in a live running application, you can read memory while the module is operating, you can do actual hardware debugging instead of guessing from UART print statements. Most locked BLE modules give you UART as your only programming interface. UART means you can only write firmware through whatever bootloader the manufacturer installed, assuming they exposed the bootloader at all. You are working inside their sandbox. SWD removes the sandbox entirely. You are writing directly to flash. You are talking to the processor, not to a middleman. Now let me be precise about what you can and cannot customize, because this is where the real engineering question lives. The BLE link layer and stack are certified and fixed. You cannot change the radio transmission characteristics without invalidating the FCC certification. That is correct and appropriate. The certification is what allows this module to operate legally in unlicensed spectrum. You want that certification to stay intact, but everything your application does with the BLE connection, every decision made above the HCI layer is yours. You can define your own GATT profiles. You can write custom services and characteristics. You can implement your own connection management logic, define your own advertising behavior, set your own connection intervals, handle your own pairing and bonding procedures. You can write a completely custom sensor fusion algorithm, a flight controller firmware, an autonomous navigation state machine, a mesh network protocol that runs on top of BLE connections. All of it running on the M4 core, all of it fully open, all of it flashable over SWD in a matter of seconds. The factory firmware we ship is a working reference implementation. It handles the RFOXiA Connect app integration, the sensor data streaming, the BLE chat functionality, the motor control interface. You can read that firmware, understand it, modify it, or discard it entirely and write something new from scratch. The choice is yours because the hardware belongs to you. This is the part the industry finds uncomfortable to say plainly. Most commercial modules are locked because unlocking them costs the manufacturer control. Unlocked firmware means a builder can make the module do something the manufacturer never anticipated and never gets credit for. It means builders stop depending on the manufacturer's update cycle. It means bugs get fixed by the community instead of by a support ticket system that resolves in 6 to 8 business weeks. Locked firmware is not a quality decision, it is a control decision. The Multinav Pro plus BLE module is FCC certified. The certification covers the RF design, the antenna, the transmitter output power, the spectral emissions, everything the regulator actually cares about. Your application firmware running on the M4 core does not affect any of those parameters. The certification is intact regardless of what you build on the application layer. You get the legal certainty of a certified module and the engineering freedom of open source. Those two things are not in conflict. They never were. If you are building a custom drone control protocol, you can write that firmware. If you are building an industrial sensor node with a proprietary data format, you can write that firmware. If you are building a mesh communication system, a wildlife tracker, an autonomous marine vehicle, a search and rescue. So that is the architecture, the dual core split, the open application layer, the SWD interface, and why locked firmware was never a technical requirement. Now let me show you the actual hardware. This is the range this open firmware runs on. Up to 50 kilometers between two modules, 20 kilometers man to drone. The application layer you write determines how that link is used. The hardware gives you the distance. 2 megabits per second data rate. When your custom firmware needs to push sensor fusion data, telemetry packets, or control frames at speed, the radio link has the throughput to support it without artificial rate limiting from a locked stack. The STM32WB07CCV6 is the reason open source access works here. The Cortex M0 Plus handles the certified BLE stack. The Cortex M4 is your application core, fully open, fully writable over SWD and separated cleanly from the radio firmware. 57 by 47 millimeters. The module is small enough to fit inside a drone frame, a sensor enclosure, or a handheld device. The fixing frame holes at 51 by 39 millimeters make mechanical integration straightforward without custom brackets. The application firmware you write on the M4 core has full access to the module's 4 interface buses, GNSS, sensors, motor and battery management and programming. Your firmware talks to the full ecosystem through these interfaces. The factory firmware ships with RFOXiA Connect app integration built in. You can use it as a starting point, modify the GAT profiles to match your application, or replace it entirely. The SWD interface makes reflashing take seconds, not minutes. BLE chat, a direct internet-independent communication between module users, is implemented entirely in the open application layer. If you want to fork it, extend it, or replace the protocol with something purpose-built for your use case, the source is there. Open source and SWD programmable, this is the specification that matters most on this board. The ST-Link programmer interface exposed here is your access point to the M4 core. Everything your application does starts at this connection. The RTC crystal provides precise timing across reboots and sleep cycles. If your firmware relies on scheduled transmissions, timestamped sensor logs, or synchronized multi-node behavior, the RTC gives you the hardware foundation your timing logic requires. And if the firmware you need does not exist yet, the AI firmware builder inside RFOXiA Club will generate production-ready code from a plain language description of your application. You describe what the module should do. The system writes the firmware, you review it, compile it, and flash it over SWD. The Multinav Pro plus BLE module gives you complete open source access and SWD programmability so you can build exactly the firmware behavior your application needs instead of being constrained by a manufacturer's closed ecosystem.
Soldering iron at 2 a.m. Schematic on the wall. Every trace a decision. Every signal a call. They said the range was impossible. They said the price was wrong. I mapped the RF landscape and I built where I belong. No towers holding me, no infrastructure fee. Just fixing intention and a module that runs free. We are the makers, we push the signal past the edge. We build the future with our hands, on every rooftop, every ledge. 50 kilometers of silence and the data starts to flow. We are the makers, and we built this from below. From below. The firmware writes itself now. Describe it, watch it run. AI speaks the language of what we have begun. Sensors streaming in the field, earning while I sleep. Every note a heartbeat, every death set mind to keep. No limits, no permission, this technology belongs to us, and everything we build is true. 20,000 meters, and the signal holds its ground. No internet, no towers, no infrastructure found. Just a model and a maker and a vision that was real. This is what democratize means. This is how we feel.